So disclaimer number one, especially for a general audience that hasn't seen before, I'm very, very infamous for speaking quickly. If you were to guess that I had more than 80 PowerPoint slides for a 40-minute time slot, you would be correct. So I'm throwing that out there. Quite a bit of my slides are more reference material, but also for a general audience, I'm sort of unsure of what key areas that the audience is interested in. So I tend to err on the side of the kitchen sink, and I throw a lot of topics at you. I'm happy to discuss them afterwards. The slides are already online in case I go quickly through something that you are particularly interested in. The other thing to mention is that, I guess technically I'm a suit, and it's important to sort of call that out, particularly because of the sort of heavy, presence of university and academic folks here. The reason why it's important to mention is that the fact that I work in sort of more commercial or industrial life science environments tends to influence my views and what I've actually experienced. And since I'm up here talking about what I've experienced, it's important that you guys understand that I sort of come from, a more industrial setting. The other reason is that one of the reasons why I'm here today is that I actually think myself, people like James Cuff from Harvard, Ari, there's a few others here, there's a couple of bio people who I think are here today as kind of the advanced guard of what I think is going to be a sort of tsunami of biologists that are going to descend upon the internet too and the high scale networking community over the next couple of years. So I wanted to introduce myself, tell you that I'm a suit. I'm from the industrial side of things, and there's going to be a lot more people like me coming to meetings like this 2015, 2016. So a little bit more about why I'm here and why I'm not actually up in Maine trying to get some work done. So the fact of the matter is, modern day informatics, any type of biology right now, essentially the IT infrastructure is the lab bench. You can't really do interesting systemic biology or genomics without a very sophisticated IT infrastructure. The second reason is that I didn't really tell you about my business, but I'm sort of a consultant who does independent and objective work in this space. And what that means is that I'm in and out of 20 or 30 different organizations every year. I get to see how different groups of smart people tackle similar problems, and most of my customers allow me to talk about what I've experienced. So I get invited to events like this because I can sort of share war stories and sort of real world. I'll even tell you when I screw up. But the main point is the red one up on the slide, which is that I'm looking at the things that gave me the biggest pain in 2014, and I'm sort of forecasting down the road 2015, 2016. For me, the single biggest pain point problem that I've got and my clients have really involves petascale data movement, petascale data sharing, and petascale data computation. And bluntly speaking, ESNet and InfiniDebt too have actually helped me solve that in a couple of my sort of early adopter customers, and I think it's just going to get bigger, broader, and more popular as time goes on. So the first plug I have is that my biggest regret about this talk right now is that I didn't get to put enough biology or science into the talk. I'm going to be sort of very dry and sort of shotgun IT trends and stuff at you. So my colleague, Dr. Ari Berman, is here. He and I we're similar enough that we steal each other's PowerPoint slides. And if you want a similar talk but with more of a focus on the use case and the biology, Ari's going to be doing a talk at 3:30 today. So you can sort of get a sort of more science or use case focused view of our world. And the other cool thing is I spent a lot of time talking about how I'm industrial and corporate. Ari does most of his work in the large spaces of very large government customers and very large organizations like that. So Ari can also speak more towards the sort of large government lab view of how things are happening right now. So my second plug is, unfortunately, I'm doing the 10-minute tech talk tomorrow after this talk. So I've got to take the 80 slides and distill them down to about 4 slides for tomorrow. So if any of you here, if there's anything particularly interesting that you hear today, if you want me to make sure that I mention it tomorrow in the 10-minute abbreviated version, I'd really appreciate a tweet or an email to help me get this thing down to 10 minutes for tomorrow. So moving on, a little bit of a quick hit of some of the topics I want to cover. And like I said, I really do want to stay on time, so I'm going to try to sort of throw the kitchen sink at you, and I'll go very, very quickly. So to sort of set the stage, the reason why I'm here, the reason why doing IT in a life science environment is so interesting is that since about 2000, we've been buried in laboratory instruments that can generate terabyte volumes of data. And these laboratory instruments are dirt cheap, and they're getting dirt cheap every day. They're easily within the grasp of a single PI, a single researcher, even with a modest grant. So these aren't showing up in just the Beijing Genome Institutes or the Broads or the Harvards. These large-scale terabyte instruments are showing up in the smallest distributed, most remote satellite campuses you can ever imagine. I'm going to show you a lot of picture of genome sequencing machines because that's kind of the sexy area of the technology right now. But it's not just genome sequencing. This is everything from a confocal microscope to an HD camera that someone's putting on a mouse cage so that they can sort of programmatically determine mouse movement and mouse moods. This is an old school picture, taken from the mid-2000s. This is one of the earlier Illumina genome analyzer platforms. But the reason why I have this picture up is take a look at what's under that. Already back in 2000, we were stuffing 24U server cabinets into a wet lab to support the IT requirements of these sort of emerging high-scale instruments. So I'll go a little bit quickly through. This is a more modern instrument, this PacBio. It's about the size of a smart car. Scientists still can buy them cheaply. They don't quite understand that they require 208-volt electricity, 30-amp power leads. So they typically buy them. They sit on the loading dock for a couple of months until the facility people catch up. The other problem I have is that the scientists who are buying these things live in this magical world where storage is infinite and free and magically appears when the device shows up. And it's a very, very common problem in my world for the scientists to buy this instrument with no thought at all over data storage or the compute environment to support this. So again, this is why I like my work. Computers are boring. Computers combined with smart people doing kind of cool stuff is really where I sort of get the most enjoyment out of my career. So this is really what I wanted to show you here. This is sort of, if there's a standard right now in the genome sequencing community, it's sort of the Illumina platform. We've got 3 different sizes here. I won't really talk about them. The next thing coming up, though, is that Illumina made an announcement. If you are willing to buy 10 of these things and invest many, many millions of dollars, they theoretically, with a couple of asterisks, have the $1,000 human genome at 30x coverage. The caveats are interesting. The caveats are that you can only get to a $1,000 human genome at 30x coverage in this system if you basically run this fleet of 10 instruments 24/7, 365 days a year. The interesting thing about that is that that doesn't fit for a lot of my pharmaceutical and biotech customers. It's a perfect fit for a university or a research organization. So what we're starting to see is my private sector biotech and pharmas are thinking about partnering with universities to go in on a 50-50 ownership share of one of these systems. As soon as you start talking about that, these things put out terabytes a day, terabytes an hour, whatever. If we're now in a scenario where a pharmaceutical company in location A in the United States has a 50% share of this platform with a university that's across the country, I've got a petascale data movement problem. So again, this is sort of why I'm sort of throwing out genome sequencing platforms right now. The other thing here, this is really what's coming. That is a USB-attached genome sequencing platform. There are people in the room. If James Cuff is here, he's one of the people who I know from his Twitter stream and Facebook feed has one of these things sitting on his desktop. So I think maybe the most interesting point to say is that the rate of innovation and sheer brilliance that's being put into the genome sequencing platforms in this, it's absolutely amazing, and it's proceeding at a pace that it's even faster than the Moore's Law stuff we've seen in the IT space. The rate at which people are doing fundamental changes in sensors, microfluidics, and how they're doing the chemistry, the fact that we went in a couple of years from these sort of big bus-sized systems to the next generation of nanopore sequencers, basically attaching via USB cable to your laptop. It's just an amazing time to be doing biology. It really, really is. At the downside, this is frankly terrifying for someone who does IT. All right, so you get my animation back again. I can't, you don't do a science talk without a scary PowerPoint slide. So this is just showing you how rapidly the cost of genome sequencing has gone down, and they try to graph it against Moore's Law to show you just how ridiculous the curve is. So this is the cost of acquiring 1 million bases of DNA off of a sequencer. This is where they've done the same calculation for doing a cost per human genome. That rate is not changing, and it's causing major, major systemic issues with compute, with storage, with networking, with data movement. The main story that I like to say is that if the genome sequencers are being commoditized. If a genome sequencer becomes 50% cheaper, the scientists don't just bank that savings, they just buy 2 of them and do twice the work. So the commoditization is killing us, because as these machines get cheaper, people just buy more of them and use them promiscuously. So we went from a terabyte scale problem to a petabyte scale problem, even in some of the smallest labs. So this is a little bit of an introduction to sort of why I start these talks with talking about how it's kind of a risky time to be doing information technology or IT in life science. The meta issue that I face is that even my most best-funded biotech customers can afford a major infrastructure refresh every 2 years, every 3 years. The pharmaceutical companies, 3 to 4 years. The slower, globe-spanning companies, 5 to 6 years. We have to design IT infrastructures that can support this sort of petascale emerging science, and these infrastructures have to survive 2, 3, 4, 5 years down the road in the face of a scientific environment that's changing every 6 months. I can sit down with the scientist and I can ask her what she's doing today. She'll be able to answer it fine. If I want to ask her what she's going to be doing 9 months or 18 months from now, she can't really answer that. The field is moving so quickly. So my central meta problem right now as an IT or infrastructure nerd in this space is that the science changes every 6 months, but I can only build a data center or do a major IT refresh every 2 years if I'm lucky, and more realistically, it's every 3 to 4 years. So that's the sort of central dilemma. And I've already talked over this slide, so I'm gonna go quickly. We need to design systems that can do unknown science 18 months, 2 years, 3 years down the road. The easy period is over. In the early 2000s, I could shove computers and storage in a network closet. I could put servers next to someone's desks. In a wet lab, I could put a bunch of stuff. It doesn't work anymore. It hasn't worked for a very, very long time. This is sort of the new scale of IT infrastructure that we're using to support biologists. This is about 2,000 cores and 2 petabytes of disk supporting maybe 18 scientists. So that's the level of infrastructure here that we're talking about. I've already talked about this thing here. Like I said, the pace of advancement in the wet lab and on the instrumentation side is just blowing away what the IT industry is doing with disk drive platter capacities or CPU cores in a single chassis or things like that, or even network speeds. So we're still being caught by surprise. I love this picture. This is what happens when IT doesn't do their jobs. The scientists go out and they buy a rack and they stick it in the wet lab. What this picture doesn't show is that this cabinet is sitting underneath the chemical bath shower. So, not a particularly proper way to do things, but scientists are smart, they've got money, they've got access to funding. If IT doesn't solve their problem, they're going to go out and solve the problem in their own special, unique way. So the other side is that you can't really blame the lab side for it. The regulatory environments, the rules, the sort of bureaucracy hasn't caught up to what we can do with virtualization, with software-defined networking, with DevOps, and with the sort of 100% virtual environment that we've got with the cloud. So we're basically operating in an area, particularly in the regulated space, where we think we have the solutions moving forward, but the rules haven't quite settled to the point where we can sort of be accurately concerned that we do actually have the real solution. So related to this, and this is another nasty problem, and I sometimes trip over the words when I say this, it has never before been as easy for a scientist to either generate or acquire vast amounts of data. And the friction for that scientist, for her to acquire vast amounts of data, it's easier for her to do that, and she's doing it at a rate that exceeds the rate at which manufacturers are making disk drives bigger. So I'm trying to explain it. Basically, we are acquiring or making data that, if you graph it out, is growing at a rate that's way bigger than storage vendors are making storage products bigger. So there's an inflection point. Something's got to break. It's a very, very nasty problem. For a very, very long time, I do have these conversations all the time. We sit down with the scientists and we explain to them the true cost of keeping scientific data available and safe and online. And oftentimes we can go back and we can do the math and we can show the proof that, look, destroy the data, delete the data, throw the data away. If you ever need it again, we can go back to the -40 freezer, pull the sample again, repeat the experiment. It's actually cheaper to go back to the freezer and repeat the experiment than it is to sort of go into this world where you have infinite storage forever and anything a scientist generates forever and ever and ever is online forever. The problem is that it is absolutely and wildly inappropriate for IT to decide what scientific data gets deleted. So that decision cannot and should not come from the IT side. It has to come from the scientists. But the scientists are in a world where their mental concept of a terabyte of storage is the $80 drive that they see at Staples or Best Buy. So the scientists are working under often a flawed assumption that storage is infinite and free, and if it's not infinite or free, it's cheap and easy to acquire. They really don't understand the real costs of keeping hundreds of terabytes or petabytes of data online, safe, replicated, and backed up. They're not stupid, though. So what IT has to do is you need to sit down, you need to engage with the scientists, you need to have the conversations, and when you do it right, the scientists become your best ally. And it's the scientists who make the data triage decision. It's the scientists who decide, yeah, I'm going to delete the FASTQ stuff that's coming off my sequencer because I can just go back to the freezer and repeat the experiment if I ever need to go back to the intensities or the color space data again. So the future's not really looking all that easy for the people who aren't prepared for this sort of nasty bit of problems that we've had. The risks are high, but they're also obvious. You've got lost opportunity. You've got capabilities that your competitors or peers have and you don't. Scientists are not quiet. They're going to complain when they can't get their research done, or worse, they're going to leave and they're going to go work for someone who can actually help them get their papers out or help get the stock price up at a competitor. And eventually, if you screw this up for long enough, you're going to have long-term problems with retention and recruiting. We've already seen retention and recruiting problems at organizations which are unable to provide the IT foundation for a very well-known, computational type person. They simply can't support that person's need. That person moves on and goes to a different organization that can. So that was enough of the sort of intro. I want to talk briefly through sort of what I see in the life science space right now. A little bit on DevOps and org charts, just because it's interesting. The social contract is absolutely going to change, and it already has changed between scientists and IT. The power balance is shifting. Far more power is going to the scientist, which is where it should be. The IT people are no longer going to be the gatekeepers. We're going to be the developers and the enablers of best practices in the security model. All of the controls are going to pass to the scientists, and it's a really, really exciting time to be involved in that. So you can blame the cloud for this. A lot of the stuff from the DevOps world that you saw, the technologies that companies like Netflix and others are using to orchestrate fleets of servers on Amazon, those technologies translate really, really nicely to organizing and automating and scripting your local infrastructure within a commercial data center. So at the end of the day, if it's got an API, you could do cool stuff with it. And we're at the point now with cloud and some virtualization environments where literally everything has an API. And this concept of scriptable data center went from sort of marketing crap that I hated using to actually a real world thing and a real world useful term. It is actually possible to have and use a scriptable data center. So I've already talked about this. The only thing I really want to say about, it's clear that Puppet and Chef and Vagrant and Salt and all those other DevOps technologies, they're already trickling down into the R&D space. They're already saving us boatloads of time and effort. The most interesting thing it's going to do is have an impact on IT. It's going to have an impact on org charts. It's going to have an impact on job descriptions. And it's going to have an impact on job viability. I am firmly in the camp, I'm going to skip this slide. I'm firmly in the camp that IT system administrators who can't script or can't code are not going to be able to find jobs in the years to come. And I'm not saying you need to become a C or C++ developer. If you don't know your way around PowerShell on Windows, or if you don't know a little bit of Perl, Python, or Ruby, there's so much of this DevOps stuff that isn't really hardcore software development. It's more glue and scripting and tying together systems and parsing data. If you're an IT person and you can't code, you're either going to have career problems moving forward, or you're going to have problems advancing and moving on in your career. And I've been sort of trying to spread that. And at the same time, I'm having very similar conversations with scientists where the scientists need to understand a little bit more IT than they're really willing to understand, because more and more of their science is within this benchtop, this laboratory benchtop that is the IT environment. And I'm oftentimes needing to teach a little bit of coding or scripting to the scientists so that they can stand up and stand down their infrastructure, or actually control the knobs that control their automated infrastructure. I've already talked over this. I'm going to skip this thing. I really think the future is that the role of IT is going to be design the systems, design the architectures, test them, security test them, penetrate, run pen tests against them. Our job is going to be to create the reference architectures that the scientists go out and use. But the state of virtualization, the state of cloud, the state of automation is such that the control is going to pass to the scientists. The scientists are going to be able to decide where you run, how big you run, what expanse footprint are you going to run in Amazon or Google, how long it exists, and when you tear it down and destroy everything. It's a really exciting time. I'll skip this a little bit more of the automation. I want to get right to compute. The interesting thing about compute is that it's boring. I haven't been challenged to bringing enough computation to bear on a scientific problem in years. It's easy to understand. It's easy to acquire. It's a commodity. It really doesn't matter which particular vendor I buy my compute from. It's not hard. To me, it's a solved problem. And that's a nice thing, because I have many other problems that are much harder. It's nice not to have to worry about compute. Our standard baseline infrastructure in life sciences, your standard HPC compute farm or Linux cluster. The cool thing is that even our laboratory instruments know how to submit jobs to a grid. So you buy one of these Illumina platforms or PacBio, it knows how to talk to Slurm or Grid Engine or LSF. So boom, you've got these terabyte scale laboratory instruments that are happily submitting jobs, back to your HPC environment. The only thing that's really changed, if I wanted to give you a concrete trend, is that there's a definite movement away from blades and very, very dense servers. If you buy my initial hypothesis that science is changing faster than IT can change their data centers, and you're looking at the future, and the future is things like Hadoop and big data and HDFS, the future might involve cramming a lot of stuff into a server chassis, and that stuff could either be a disk drive or a GPU card or a coprocessor card. It's hard to stuff a lot of stuff into a blade. So if anything, the defensive hedge that I'm seeing right now is we're moving away from blades, and we're moving to 2U and 4U servers that we can stuff disk drives and PCI card devices into. Again, because we're trying to hedge and build an infrastructure that's going to be useful 2 to 4 years down the road. It's a little bit harder to do that in a blade environment. Practically speaking, at large scale, what we're doing is we're running mixed. We have a rack of high-density compute CPUs sitting next to a rack that we keep relatively open so we can put beefy servers in. I'm going to, this is just a shout out to ESNet. I do have workstations that are heavily involved in physical data ingest. Everybody jokes about the disk drives being moved around via FedEx. That's an everyday occurrence in my world. We now have 10 gig NICs going straight to our data ingest workstations. And ESNet has been telling me for years all the things you have to think about when you've got 10 gig going to the desktop. And there's a lot of cool training stuff. And we've hit every single problem that they've talked about. And now we're very, very careful about our NIC selection, our kernel parameters, how we wire them, and how we use them. So again, I am continually thankful for the amount of free education and technical materials that sort of ESNet and Internet 2 have been sort of regularly publishing out to the community. It's fantastic to see. I benefit from it every day. I'm going to skip the diversity stuff. At large scale in life science, we've turned our HPC environment into building blocks. We have the compute block, we have the block for GPU, we have the large memory blocks. We do have some of us have needs for very, very large memory. If you're doing de novo human genome assembly, you probably need a node with a terabyte or 2 of RAM, so we need to sort of build that into our environment. Again, there's all sorts of interesting PCI cards popping up. It's nice to have chassis that will accept them when we need them. I will be a little bit cynical and say that I'm less convinced in the world-saving powers of GPUs and FPGA cards and coprocessor cards, simply because the activation energy required for a scientist to use them is still high enough that they still tend to favor general-purpose computing environments. You only see these specialized PCI card devices in high-value, high-throughput environments where it makes sense to architect and engineer specifically for that coprocessor or specifically for that GPU. There's some exceptions, chemistry and others, but in a general sense, the activation energy required to use a PCI device is relatively high for a general-purpose scientist who just wants to get her work done. Hybrid HPC, the only thing I really want to mention this is that I used to be one of the people, I'm very cynical and blunt. If you asked me about hybrid clouds or private clouds 2 or 3 years ago, my response was utter crap. It was 100% marketing over reality. That's absolutely changed. We're doing hybrid clouds now, they're real. What has enabled that is actually the ease at which we can acquire high-speed bandwidth. Until we got high-speed bandwidth outside of our buildings, the hybrid cloud stuff, the private cloud stuff, it was just a neat trick, or it was kind of cool to do for a demo, but the utility was less than the marketing hype would suggest. A little bit on the network side, it's one of the reasons why I'm here. So for me, this is one of my biggest pain points problem coming on ahead. So for me, 2004, 2005 was an era where compute was a problem, when we were all frantically trying to build clusters in architectures that would solve the compute side of bioinformatics. A little bit down the road, because of the sheer amount of data coming off these instruments, I had a massive problem in the late 2000s just dealing with hundreds of terabytes to petabytes of data. Now, Petascale Storage isn't really scary or sexy anymore. There's half a dozen vendors that if you pick up the phone, they'll ship a petabyte usable NAS or block storage to your loading dock in a week. 10 years ago, it was a risky endeavor. You were betting your career that the Petascale Storage project would succeed. Now it's just an appliance you can buy off the shelf. So really where I'm at right now is petascale scientific data is really useless if you can't move it around, share it, and compute against it at fast speeds. The problem is that we don't see the commoditization gains at 10 gig, 40 gig, and 100 gig that we've seen with compute and storage and everything else. It is still ridiculously expensive to acquire the sort of high-speed networking that we need. And the problem is that I suspect it's a little bit easier in the university environment where there's more openness to interesting vendors. I'm locked in a world where I get thrown out of the room if I say anything other than Cisco. And so it's very difficult to sort of wedge these requirements in. So again, I've talked over this slide, is that my gut feeling right now is, so I had a problem back in 2004 where as a single scientist, I had more compute and more storage than the entire organization had as an enterprise, just for me doing my biology. That same problem is going to happen now in the life sciences when it comes to NIC and port speeds. We're now going to have a small group of biologists who have a definite business need for 10 gig, 40 gig, and maybe even 100 gig, and that need eclipses what the enterprise is running at their core. And the problem is that with compute and storage, I could sort of run a silo. I could run a cowboy data center environment. I could build my own crap and run it. I can't build my own 10 gig, 40 gig, and 100 gig infrastructure without the active participation of the security folks, the risk management folks, the network engineers. And those are the folks that have been using Cisco for 20 years, and those are the folks that, they don't like Science DMZ. They look sideways at me when I say perf sonar. It's just an interesting time to be trying to wedge this stuff into the enterprise. And that really, the reason why I'm here is that I think this is my pain point, and this is why you're going to see more and more biologists coming to these meetings over the years, is that we as a community now need networking speeds above 10 gigs, and the corporate and the institutional networking people that traditionally support us, they're not there yet. They are not there in attitude, they're not there in budget, and they're not there in capability. One quick real-world example. I've got a pharmaceutical company right now. They've got all their scientists sitting happily at one site. They've got all these terabyte-scale instruments sitting at that same site. They've got 2,000 cores and 5 petabytes of disks sitting halfway across the country. They're doing replication to a third site. At the same time, they're looking down the road at the future, and their future is very, very collaboration-heavy. And in particular, they're going to be collaborating with people that are competitors in other areas. The other thing is, this is the pharmaceutical company that's kind of talking to universities about sort of joint ownership of that Illumina X10 platform. So how do you handle that problem where your scientists and your instruments are in one site, you've got all your compute and storage at another site, and by the way, you're looking at a future that is collaboration-heavy with some sensitive security needs, and you might be buying a share of a multi-million-dollar genome sequencing platform that's also halfway across the country. So in this case, it's Internet 2 and Amazon to the rescue. This is hopefully a generic slide. Hopefully you won't see any company names in there. I was pretty careful about it. But what we're actually using is we're using Internet 2 AL2S to get 10 gig connectivity into Internet 2. We're then using Internet 2 to deliver us to a 10 gig port at a particular data center in Virginia, where Amazon happens to expose their Direct Connect service, so I can get 10 gig straight into Amazon. I've got a fantastic infrastructure out there. I've got all of my scientific computing running in Amazon, which solves a couple of different problems. It allows me to ingest or share data very, very easily. This is also the place where I do my hairy collaborations, because I have no problem spinning up a custom cloud footprint to handle a collaboration with someone who might be a competitor. There is no way in hell I'm going to allow that competitor into my Active Directory or into my firewall. So one of the big drivers behind cloud adoption in the life sciences is that, from a cynical perspective, people are viewing infrastructure cloud platforms as the neutral meeting ground. It's the safe place to do collaboration and share a little bit without inviting your competitors into the firewall or creating IDs for them within your federated identity management system. So the other thing I want to mention, and I'm sure there's probably vendors upstairs that are looking at this slide and are absolutely guaranteeing that they can save me 6 figures worth of money. This is what I had to agree to get an Internet 2 connection into a pharmaceutical company. This is probably 4 times more expensive than the cost of the 10 gig circuit to Internet 2. They want full checkpoint. They want every single network security control that they currently run within their corporate LAN. They need it to be applied to this thing. They might even force me to buy another one just to protect the business from the scientists. It's not cheap, but in the interest of getting science done, I think the only win I have on this slide is you can see 2 or 3 perf sonar boxes. I managed to get those approved, but there's a heck of a lot of expensive Cisco stuff in this mix, and I actually want to go up to the vendor booths upstairs and sort of see how much money I left on the table by agreeing to this. I'm going to skip the gut. My gut feeling about Science DMZ right now is that if you look at the reference architectures and what they're doing, it's a little bit more complex than what we can realistically put in a commercial environment. In particular, the stuff about bypassing firewalls for high data flows between trusted parameters, between trusted endpoints. My gut feeling is that we're going to do it. It's just going to take us a long time to get there. And what I'm trying to do is I'm trying to sort of prime the pump. If I could get a couple of perf sonar boxes in there and preach the message about proactive network monitoring and troubleshooting. If I can get perf sonar in 2014, then maybe 2015 someone will actually let me talk about bro in a network security context instead of checkpoint or anything else. So baby steps, I think we're going to get there. I'm a little bit worried I'm going to lose some friends by saying this. I'm fairly cynical on the state of software-defined networking, even after sitting through the announcements that were made this morning. When I started looking at SDN really closely, I read through it, and at the end of the day, I was like, all right, so you get an API that controls port forwarding behavior on a switch. Big deal. I think my take on it right now is that the level of effort required to deploy software-defined networking in a production corporate environment, it's not worth the effort and cost right now. I guess that's the easiest way to say it, is that I'm not going to change out my existing networking environment just to get an API that controls port forwarding behavior on a switch. That's not enough. There's too much work. There's too much money involved. I don't have the right people to deploy it anyways. So where I am with software-defined networking is that I think it's the future. I'm already seeing the benefits of it. One of the coolest uses of SDN that I've ever seen actually was the Internet 2 AL2S portal, where you can sort of point and click and create circuits between providers. That's really, really cool. I'm going to see that. It might be 5 or 6 or n number of years before we actually see that percolating into the corporate world. So right now, my take on software-defined networking in the sort of commercial, cynical, pharmaceutical biotech spaces, we'll see it in virtualization environments. We'll see it in proofs of concepts. We'll see it maybe touching our Science DMZs. More than likely, we're going to see it in our OpenStack rollouts. But no, it's not going to happen. It's not going to happen at an enterprise level or a production level. The return, the capabilities you gain are not worth the cost and not worth the effort to deploy at this point. So a little bit on storage. I'll go quickly here just because I've got about 10 minutes left. Storage to me also feels like compute in that it used to be a very, very scary, nasty problem. We cracked the petabyte scale storage stuff years ago. My biggest storage hassle right now is managing scientific data through its life cycle. It's no longer, oh my God, how do I actually store the stuff that's coming off the instrument? I'm going to skip some of these words here. Tiering is becoming important mainly because we've gotten away in biology with a lot of monolithic single-tier scale-out NAS infrastructures. Above 500 terabytes, if you're still using a single tier of storage, you're probably wasting more money in CapEx than it would cost you to hire a person to wrangle your data into shape. I'll skip this. I'll skip the new way. You know, the interesting thing about storage right now is that we're in an interesting time for Petascale Storage because there's some pretty cool disruptive stuff. At the very, very low end, you can take the Backblaze pod style thing, and for about 10 grand, you get a couple hundred terabytes usable. We, BioTeam, we've definitely built petabyte usable ZFS stuff on commodity Supermicro. If you take out the human cost, it's about 100 grand worth of hardware. So 100 grand for a petabyte is pretty reasonable. But more interesting is right in the middle, there's these companies like InfiniDebt. It's basically a petabyte usable appliance that drop ships from Israel with a 10 gig NIC. You buy it, it shows up. It's a really, really nice solution for cheap and cheap storage. But the interesting thing about this is that these types of products strike the right mix. They're much less expensive than buying a petabyte usable from one of the tier 1 storage vendors, but they're also a little bit more expensive than what it would cost for me to do a homegrown, do-it-myself system on Supermicro commodity that I would then have all sorts of operational and support issues. So it's a really, really interesting time now in Petascale storage simply because the wide array of product choices are out there. If you have very little money but lots of warm bodies, the do-it-yourself approach is very good. If you have money but you don't have humans to care and feed, the tier 1 vendors, to build a scale-out, easy-to-manage systems are great. And if you're somewhere in the middle, there's disruptive solutions like the InfiniDebt box out there. I'm going to skip object storage except to say that if you look at scientific data, the way we use it and the way we need to share it, object storage is a perfect solution for scientific data, particularly geographically distributed erasure-encoded object storage. It's the future. The problem is in life sciences that we have hundreds and hundreds of legacy applications and algorithms that are never going to be rewritten. All of them sort of assume the standard file and folder and path semantics for getting at a file. We're not going to rewrite our entire application mix to use object storage. So what I want to say about object storage is that it's the way of the future, but life science, because of our legacy encumbrances, we're going to be slow to move. The high-value, high-scale stuff is already moving. The trailing edge is just going to take a long, long, long time. I'll skip the rest of the object storage bits. You can't do a BioIT talk without the C word. Fortunately, I've already talked over some of these slides here. I've already said the drivers in life science are a little bit more than cost. Oftentimes, it's about getting capability that you don't have natively on your bare iron. We have laboratory, and this is the sneaky, I really got to, give props to the marketing people for the instrument vendors. The instrument vendors can now natively write to the cloud. That's a great way for a scientist to completely do an end run around IT. Put your credit card into Amazon, put the S3 keys into your instrument, and boom, all of a sudden your instrument is writing to a remote cloud store, and IT has no idea what's going on. I've already talked about this thing here. Again, this is the driver here. This infrastructure hanging off of Amazon is that this is what allows me to exchange data with peers. This is what allows me to collaborate with people that I don't necessarily trust inside my firewall. And oh yeah, the economics are particularly compelling as well, particularly in some storage and file sharing use cases. I'm going to, the IAS Cloud, I used to be, like I said, I was fairly cynical about private clouds, but not so much anymore. They're real, they're useful. We're doing stuff, I think OpenStack is where we're putting most of our pennies at this point. We're starting to see a bunch of pilots, successful pilots among our clients and customers. I still think you have to be a little bit cynical and dive through the marketing to sort of figure out if it's worth your effort. I still think that infrastructure cloud platforms, whether it be Google or Amazon, it's a better bang for the buck relative to what you have to invest in time versus money. The only other thing I want to say is that I have a long history of saying anybody other than Amazon is a delusional pretender. Amazon has a multi-year technology and product head start against even Google and Microsoft, particularly if you're like me when you look at infrastructure platforms from a building block perspective. Amazon has 100 building blocks. The other competitors have a couple. But the interesting thing that's really changed this year is that Google became viable. And Google is very, very interesting from both a cost model, from a hardware capability model, and from some of the networking stuff that they're doing. So my cynical take right now is on the infrastructure cloud platforms, I only play on 2 clouds, primarily on Amazon, and then when the use case matches it, Google is legit and Google is real. Most of the other competitors are delusional, and I'll have to say one of the things that I really have a problem with is that there's way too many companies that put a marketing lipstick layer on top of VMware and call it a cloud. That might have been cool 10 years ago. It's frankly embarrassing now. You sort of have to step up your game if you're going to call yourself a cloud provider in 2014. So a little bit ahead, actually, I think I might end with just about right on time. So I want to talk about what I see sort of coming down the road. We are long past the point where scientists need to get off this file and folder-based storage system. There are so many other things about data that I need to understand besides owner, group, read, write, and execute. I need to know what scientist owns this data. I need to know what grant paid for the generation of this data. I need to know the retention requirements of this data. And I need a secondary contact for when the first PI, when she leaves and moves on, who's the second person who inherits the data. It's a real pain in the ass to do that with a standard file system these days. The solution might come in the form of these sort of metadata-aware storage systems. iRods is one of the competitors, that's sort of out there. I actually really think, there are other industries that have solved this. If you think about the media asset library that, a television company or an ad company has to manage, all sorts of tag value pairs associated with big binary files, someone has solved this. They just need to slap a biology label on it and sell it to the pharmaceutical world, and we'll be happy. But right now, I think iRods is where it's at. The other thing that's happening is I used to think there'd be a lot more virtualization going on. Where the scientists are going is with Docker and containerization. It is far more likely that I'm going to be slinging Docker containers between my local cloud and Amazon, or Docker containers between my local cloud and Microsoft. It's far more likely that we're going to be moving application containers than VMs these days. That's pretty much the future. I'd say, of my clients, maybe 2 or 3 are piloting Docker at this point. It's one of those things where, again, it's sort of the early edge of the trend, but you'll see a lot more of the containerization stuff. In particular, BioTeam is doing some really interesting stuff. My more nerdy colleagues within my company are just blowing me away with what they're. It makes me feel old, unfortunately, with what they're doing with Docker these days. The other thing that's happening, and I just want to mention the storage stuff, is I feel where storage is kind of a solved problem, but there's a lot of interesting play in the Petascale storage space at the low end, at the medium, at the high end, and it's going to be interesting to see kind of who wins and who gets the market share. The days of sort of scale out now as being the clear winner, might be over. It's going to be interesting to see a mix of what's out there in the real world. I really want to fixate on networking. We really do need stuff beyond 10 gig. And the problem is that even though we know we need it, we typically, it's harder and harder to have these conversations with the enterprise networking folks. Like I said, sometimes there's a political problem, sometimes there's an ego problem. They don't like the fact that 2 scientists sitting over in a lab now need 40 gigabit when the entire organization was running on a 10 gig core. It's sort of an ego thing to realize that the scientists have a bigger need than the enterprise core does. But at the same time, it's a more practical thing. I can't talk Arista or Juniper or any of these other sort of interesting technology brands out there at a shop that's been Cisco for 10 or 15 years. It's very, very difficult to have these conversations. And my biggest pet peeve is that relative to the amazing commoditization rate of instruments and storage and compute, this networking stuff has not gotten cheap. If I was offered a free 100 gig port on Internet 2, I would say no, simply because I can't afford the optics and the line cards to connect at 100 gig speeds. And they have not gotten cheaper at the rate at which storage and other things have gotten cheaper. So there's vast room for improvement in that space right now. Longer term trends, compute continues to become easier, particularly as it's easier to buy faster bandwidth to the outside world, as I can wrap my applications in Docker containers and ship them around to run on anyone's cloud. Petascale storage is already a commodity. It's just really a matter of how you manage it. Data movement, physical and network. I didn't really talk about what a pain in the butt it is to do a physical data ingest. Terabyte volumes of disk drives arriving via FedEx. It's really easy to wave your hands and talk about it, or maybe whiteboard it. It's a fantastic pain in the ass to do it for real without losing data and without sacrificing time, effort, or accuracy. I still think the cost of storage is going to be dwarfed by the cost of managing storage through its life cycle. I'm definitely in the camp where if you have more than 500 terabytes of storage in a single tier, you're probably wasting more money than it would cost to hire a person to wrangle your data into shape. And again, I see the end of HPC stuff. I see the ends of sort of our architectures are no longer sufficient to handle the scale of the work that we're doing. The look and feel of our R&D IT landscape is going to be very, very different 2 or 3 years down the road than where it is right now. So that's it. I have 1 minute and 30 seconds left. That was 82 PowerPoint slides. Thank you very much for your time. I'm not sure if we have questions. I think if we've got a minute or two, we'll take some questions. Otherwise, my info is up here. The slides are already online. I would love to chat with you more, in particular to find out if there's any other bio folks here in the audience. So again, thank you very much for your attention. And I'm fairly blind, so someone might have to help me if there are questions out there.
I got one.
OK, yep.
So my name is Eric Puyol. I'm from ESNet.
Yep.
And you just said that you believe that that's the end of the big infrastructure, data centers. Do you think there'll be an impact in terms of the way you send data over the network? Right now, with the Science DMZ, it's mostly reads and write. Yep. Are you thinking about remote IOs, for instance, distributed file systems?
Actually, my take right now, is, at least from my view, the vast majority, the single biggest use case of these high-speed networks is going to be moving the data. In reality, what we do is we compute against the data where it lives. So if I'm going to go through the effort of moving my data to Amazon or moving my data to another place, it's relatively inexpensive and very, very easy for me to fire up the compute and do the compute in situ where it's sitting. So I think the bandwidth that we're getting from Science DMZ is going to allow us to do interesting things. I'll tell you, biologists are lazy. The first thing that we're going to do is we're going to try to run NFS over 10 gigabit Ethernet, across the country. But I think, practically speaking, our use case of the network is going to be moving the data from location to location. We will compute against the data where it rests. And oftentimes, we're bringing in the users over a very lightweight remote desktop. So you could almost think of the data as the center of gravity, and everything else, the users and the compute, flows to where the center of gravity is.
OK,
thank you. All right, I'm at 0. I think there's a flashing light, too. So, oh, sorry, one more question. Yep.
So I'm Brett Draney. I'm at NERSC, and we're basically the cloud provider for the Joint Genome Institute. So we've implemented a lot of what you've got here.
Yep.
I'm interested in your take on metadata and bio, because that really seems to be the corner of the box that is tripping up the bioscientists, is dealing with very small ASCII files and millions of them. I see in our compute platform, most of the compute is just about I/O processing and not about actually computing science results.
So metadata ties into that whole iRODS thing. So the interesting thing is the people who've been most successful at rolling out metadata-aware file systems are also the sophisticated shops that are able to employ engineers who can actually hack the iRODS system. So you see iRODS in heavy use at EBI and some of the sort of larger genome consortiums. The problem is right now is that there's no easy metadata-aware scientific storage data system that sort of mere mortals can, not mere mortals, but if you're buying into the metadata storage world, you're basically going to have to buy into some headcount as well. You have to buy some engineers to control it. On the operational side, I would say the cleverest things that I've seen done with metadata is that metadata is another area where it's inappropriate, or oftentimes IT can't provide the metadata. We need to collect the metadata from the scientists. Some of the best methods I've seen come from like Harvard and the Broad Institute, where they use the carrot and stick approach to socially engineer their users. They will give the users unlimited storage in a very slow environment. They will progressively give them greater and greater quota on faster storage as they tag their data and provide metadata. So I'm in the camp where I like to socially engineer my scientists, and I give them carrots if they're willing to describe their files and data and retention periods. And if they're willing to do that, there are institutional things we could do to reward them for that good behavior. And that typically means moving them or removing their quota or allowing them to play on a much faster storage system. Scientists get mad when you force them to do things, but you can sometimes sneak them in, I guess is the best way to say it. All right, thank you very much.